Várilly-Alvarado's second lecture.
Thanks a lot. Thanks for being here. So I'm going to use roughly this clock. It's 10:07. I'm going to go for about 50 minutes. Okay, so today I'm going to leave the world of just pure geometry of what we were doing yesterday and start talking a little bit about arithmetic of K3 surfaces or things, problems over number fields. And we'll use things like reduction to finite fields to say something about the ranks of Picard groups. So that's the idea. So let me start by setting some stuff up and reminding you. So X is going to be an algebraic K3 surface. So this is going to be over K, and K is going to be a number field to begin with. I should say, so I want my surfaces. Yesterday I was working over an algebraically closed field, and so I said integral, and now I'm not going to be working over an algebraically closed field, so I want geometrically integral. And so my K3 surfaces satisfied two conditions. They had trivial canonical class, and the H1 of OX was 0. So these were the surfaces we started looking at. And by X bar, I mean the base extension of X to some separable closure of K. And as we just saw in Coletalen's lecture, sort of at the beginning of the lecture, he noted that using this spectral sequence, you could see that the Gallum module structure of pic X bar, I should say, so encodes, this is sort of a vague statement, but sort of arithmetic on X. And so, for example, the algebraic Brouwer group modulo those pesky constant algebras coming from the ground field, we saw that this was isomorphic to this H1 of Galois acting on pic X bar, provided, for example, that you have some local points or something like this. So, but this is the sort of assumption we actually want to have, because if we don't have local points, we sort of close up shop and go home. So, okay, now it would be great to be able to say something about this Gallum module structure of pic X bar, but we're going to start with a much more basic question, which is, what's the rank of this thing as an abelian group if I start with a K3 surface over a number field? So the question that I want to sort of take a look at today is, what is the rank of this pic X bar? And we were calling this rho of X bar. Okay, so we saw yesterday, when we studied complex algebraic surfaces a little bit, that, so recall that, okay, so first of all, I didn't have to worry very much about the distinction between Nernst-Severi, pic, and num. And in fact, this number was at most 20. It was sort of bounded by the H11 Hodge number. And for complex surfaces, it was at least 0, but I'm looking at algebraic things that are in some projective space. And so there's some ample class. And so it's going to be at least 1. And so the question is, okay, so there's a lot of room in there. So what is it and what can it be? And that's what we're going to look at today. So the first tool to study this problem, which I want to develop, is sort of reduction mod P, mod P, or specialization. Which is to say that we can sort of take, if I have some prime of good reduction, what I want to do is look at, reduce modulo of that prime, and so now end up with some surface over some finite field, and try to calculate the Picard rank of that and relate it to the Picard rank of the original K3 surface. So to do that, I have to just pause and make sure that we're all on the same page. and review what good reduction means. Okay, so naively, and this is sort of, mod of finite prime p of my number field. I mean, we sort of think of it as, you have these bunch of equations in your projective space, and you're going to, clear denominators, reduce mod p, and hope that, you have something smooth. That's sort of the naive thing that you might think. But then bad things can happen. You go to sleep, and some goblin comes around and like multiplies all your equations by p. And then, you wake up in the morning and you reduce mod p, and you get 0 equals 0. And that's smooth because it's the whole ambient space. So, but that's sort of not really good. And that's sort of, if your goblin is not a rookie, they can do way worse things to your equations and still make them look bad when you reduce mod p. So let's actually sort of make sure that we're all on the same page here. So the setup is R is going to be a Dedekind domain. Okay, with a fraction field K. R, there. Okay, so, and I'm going to take P, it's going to be a non-zero prime. And X is going to be a smooth, proper K variety. Okay, and so good reduction at this prime P, what it's going to mean is that there exists a smooth, proper morphism. So from a variety mathcal X, or X, to spec of this localization at P, such that when you look at the fiber over K, this is isomorphic to my original X as K schemes. Okay, so that's the official definition. Let me draw you the picture of, this is sort of, I think this is a picture my advisor drew for me 100 times when I was a graduate student. So, all right, so I'm gonna have my spec RP. Now, this thing was a Dedekind domain and I've localized, so now I have this nice DVR, and so I have this nice point, my generic fiber, and then I have the closed point, so spec little k. So little k is the residue field. Okay, and this is going to be my X, and so I'll have this nice generic fiber, and I'll have some special fiber, and this is xk, and what we want is that this is our original X, and this is sort of what we'd call the reduction of X. So this is the fiber above little k, which we'll call usually X sub p for sort of obvious reasons. So when we talk about primes of good reduction, sort of implicit is the existence of this X and sort of all this little data here. So, all right. So now, related to this, I'll introduce specialization. Which is meant to immediately remind you of the picture that I just drew. I'll say how in a second. So here, my setup is going to be as follows. R is going to be a DVR, just like this R sub P here. And it's going to sit in my field of fractions K. And then I'm going to take some separable, so an algebraic closure. I really want to do things over a number field, so I might as well sort of start saying this is like a DVR, and I'm hoping that K is a number field. And I can take the integral closure of Rn here. And I have a residue field as well. So K is a residue field. And if I choose some prime in Rp, so this I'll call K bar, and this will be an algebraic closure for K. and P is going to denote the characteristic of this residue field, little k. And I want X to spec R. So this is going to be a smooth, sort of relative dimension 2 and proper. Okay, so now the relative dimension 2 is not so important for the specialization, but it is important for the lattice structure that I will want to preserve as well. So the idea is that with this setup, which is sort of reminiscent of exactly this one, where I've sort of replaced this R sub P with my R, there's actually a map that goes from pick X K bar to pick X little k bar. And it's sort of constructed, I mean, you do it a little bit slowly. You sort of look at finite extensions of K, take integral extensions, the integral closure of R, look at residue fields, and sort of take limits as you go along. Naively, this map is sort of the nice thing you might want. Because of the hypotheses that I have these nice smooth varieties here. And so when I look at pick, I may as well be talking about things like V divisors. And so naively, I could, the map starts with some V divisor in this generic fiber, and I just close it up, and then it's going to hit this special fiber, and then that intersection is some divisor in that special fiber, and that's this map. Okay, and in this level of generality, I've not really assumed that my X is a K3 surface or something like this, but you can still, even now, use this to produce a specialization map that'll go from Néron-Severi of the X K bar to Néron-Severi of X little k bar. Okay, and I should say, so this map in general is actually injective up to the P torsion. The P torsion is a bit of a problem, where P is the characteristic of this residue field. Now, the good news is that we're about to say K3 surface everywhere. So first of all, these picks and these Néron-Severis are going to be the same. And we saw last time that Néron-Severi is torsion-free. And so I don't really have to worry. This map is actually going to be an injection for my K3 surfaces. So let me put this over here. So, and just say the sort of conclusion of this discussion is that these two fibers here are K3 surfaces, then in fact the Picard number of my original surface, the geometric Picard number, say over the number field, let's say that K is a number field, just to fix some ideas. So this is going to be less than or equal to the Picard number of the reduction. Okay, so that's really, well, okay. We don't know yet if this is useful or not. It's a good bound. So, I know that this is what I want to calculate. I know that it's bounded above by the Picard number of what happens when I reduce mod P. And I look at that geometric variety. So I pass to some algebraic closure. So, okay, this is only going to be good if we can actually say something about this number instead. Okay, so that's the next step. So first step is we bound the number. Now we have to say something about this one. So this is where the other tool that we need comes in, and this is the cycle class map. Okay, and so I need a little bit of setup. So since I'm going to be looking at these number fields, my little k is going to be some finite field. So let me start with varieties over finite fields. So I'm going to have my x over fq. This is going to be a nice variety, and by nice I mean the usual adjective smooth, projective, geometrically integral. So nice, and q is going to be p to the r, and L is going to be a prime different from P, and I'm going to look at Frobenius, the topological generator of the Galois group of some algebraic closure of FQ bar over Q, which, and I'll call this group gamma. So eventually I'll remind you, this sigma is going to disappear, sorry, yeah, this sigma is going to disappear for a little bit. This is going to be Frobenius. So, okay, great. So what we do now, so I'm going to go through sort of the setting up the argument that will allow us to get our hands on this number. It's going to involve a little bit of Italco homology. If you haven't seen Italco homology before, don't worry too much about it. It shouldn't be too difficult to formally follow what I'm saying, and then I'll try to make clear what the upshot is. So, okay, so let me start by saying that what you do is you look at, say, the Kummer, so this is L to the n, exact sequence, which is replacement in some sense. You know, now we're not working over the complex numbers. So I replace my exponential sequence with something like this. It's sort of a handy thing. And this is actually exact for the Ital topology, so on X at bar. And so that means I look at the long exact sequence in Italco homology of this thing, and I'll get some boundary map. So just formally, from X bar of GM to H2 Ital of X bar of mu L to the n. Okay, now sort of for reasons of Galois actions, I'm going to relabel this Z mod L to the n Z twisted by, so this one twist. This is not so important just yet. Now we saw yesterday in Coulter-Lenz lecture, the Hilbert 90, this is really pick X bar, so that's good. And now I have these maps, and I have each one of these maps for some n, and so I start looking at as n grows, and I can take an inverse limit as this n grows. So let's take this inverse limit, because I can relate these mu L to the n plus 1 to mu L to the n. And what I'll get is, well, the pick X bar is going to be my pick X bar. And that's going to go to some inverse limit of these things. So H2 at of X bar mu L to the n, which, okay, so when I take the inverse limit here, I'll call this, so H2 Ital of X bar, ZL1. Okay. ZL1. Okay. So, and then what I'll do is I'll tensor with a QL. Now, again, I sort of took a step back. I wasn't assuming that I was looking at K3 surfaces. So if you look at these maps and you study their kernel a bit and you look at this tensoring, sort of the correct thing to put next is actually Néron-Severi. But since we're going to be looking at using this for K3 surfaces, it's not going to matter so much. So this is going to be, in fact, an injection into H2 Ital XL with coefficients in QL1. Okay, so the idea is, I mean, this is what, you know, remember that X right now is over a finite field. So this X that I'm pointing to right now is what eventually will be the reduction mod P of my X coming from a number field. And I wanted to bound the rank of this thing. And so I'm sort of putting it instead into this group. And what we're going to do is try to sort of obtain a bound for the image inside this group. Okay, now we have to do just a little bit of untangling, and this is more a technical disclaimer than anything else, which is that this H2 Ital of X bar QL1, so this is isomorphic to H2 Ital of X bar QL 1. So I'm sort of taking this twist outside, and by this I sort of mean, so the original H2 tensored with over QL with QL tensored over ZL with the inverse limit of these mu L to the n's. Okay, why am I doing any of this? Okay, the real reason is that I mean, the way we've set it up, this twist was in here. I'm trying to sort of untangle a little bit the Galois actions that are going on. So these étale cohomology groups come with some Galois action, but then these roots of unity also have some Galois action, and I'm trying to separate them a little bit as well. If I just look at this thing right here, I'm thinking of these mu L to the n roots of unity inside some finite field, perhaps some extension of my ground field, and I'm acting on them by Galois. And now Galois was this Frobenius, which raises things to the Q. But then you have to sort of think about what the ZL structure of this inverse limit is, and sort of raising to the Q is really multiplying by Q for this ZL. So the Galois action in here is multiplication by Q. Okay, so that may take a little bit to untangle in tonight's study session, but I'll say why I just made this mess in a second, and what'll matter is really the conclusion of the whole matter. So, and before I do that, I should just say one last thing, which is that C is compatible with gamma actions. So there's the Néron-Sévère has this action of Galois. I mean, naively, what is this action? So, I mean, I write curves. Remember, Néron-Sévère and Pick are the same, so I write curves that generate this thing. These curves are going to be defined over some finite extension of the ground field, and I can apply Frobenius, for example, to the coefficients of these curves, and it'll give me some other curves, and that's going to be perhaps some other class in Néron-Sévère. So that's the action there. And what I'm claiming is that this C is compatible with sort of all the Galois actions that are lurking around. And the reason this is important is the following observation. Okay, and it's defined in a statement that I just made. So some power of the induced map that Frobenius has on Néron-Sévère of X bar acts as the identity. And why is that? Well, it's because, again, I mean, you have some finite number of generators. You write down equations for them. Everything is defined over some finite extension of the ground field. You apply Frobenius many, many times, and you'll sort of hit the Frobenius of that ground field, and then nothing will happen to those coefficients. So eventually, the sum power of my Frobenius acting on Néron-Sévère is going to be the identity. And the reason this is important is because it means that the eigenvalues of this sigma star acting on Néron-Sévère of X bar are roots of unity. Okay, good. So why is that good? Well, now we have this injection of this Néron-Sévère X bar, tensor. I mean, I guess I should really let me tensor all of this stuff with QL. So we have some nice vector spaces. And so what this means is that I'm going to look at sort of the induced action of Frobenius on this H2 instead, and I'm going to look at the eigenvalues that are roots of unity, and that should give me some upper bound for the Picard number of this NX bar. So putting things together, so we put together, what this means is that my rho of X bar, which remember was the rank of this Néron-Sévère of X bar, and if you want as a QL vector space, the QL rank, this is less than or equal to the number of eigenvalues. So we said it here, so it's the number of eigenvalues of sigma star acting on Néron-Sévère that are roots of unity. Now let me translate that into the H2, so it's the number of eigenvalues of, okay, so now the action is going to be a little, it's the twisted action on, so this acting on this H2 étale of x bar QL1 that are roots of unity. And remember that I told you that once we had untangled these twistings, on this part, Galois was acting by multiplication by Q. And so if I want to sort of, instead of looking at the twisted action, I just want to look at the untwisted action, then I should be looking at the number of eigenvalues of sigma star on this H2 that are not quite roots of unity, but roots of unity divided by Q. So this is going to be less than or equal to the number of eigenvalues of sigma star acting on H2 et al. X bar QL. Ooh, I'm writing very small. Oh, okay. All right, that are, so of the form, so nu over Q, where nu is a root of unity. Okay, good. So, I mean, we still don't have a handle on what this thing is, but I promise we will get a handle on exactly this quantity. Okay, so that's, and so we're going to combine the specialization. I start with something over a number field. I reduce mod p for a prime of good reduction. I know that my original Picard number is bounded by the Picard number of the reduction, and then if I can get a handle on this number of eigenvalues, then I'll have an actual upper bound for the Picard number of my original K3 surface over the geometric Picard number of my K3 surface that was defined over a number field originally. Okay, so what is, I mean, how are we going to get our hands on something like this? So what we want is the characteristic polynomial of this sigma star acting on this QL vector space. Okay. I also want $10 million, but we can't always get, so that's not going to happen either. So this is what we can get. Okay, I mean, so sort of being a bit facetious here, but what I really mean is that calculating the characteristic polynomial of this thing sort of directly can be kind of hard. It's a little easier to calculate the characteristic polynomial of the inverse of this thing. So the characteristic polynomial of sigma inverse acting on this thing. Now, okay, but we don't have to despair just yet, because what that means is that, okay, before I was going to look for the number of eigenvalues of this operator sigma star of this particular form, but if instead I look at the inverse operator, then all I have to do is try to find the number of eigenvalues that are of the form nu times q instead of nu divided by q. So the fact that I can compute this characteristic polynomial instead is just as good. So it's really not a problem. The other little note that I should say is that this inequality here, so the Tate conjecture, implies that this is an equality. And this is okay if Q is odd. So the Tate conjecture has been proved recently. I'm out of space, but there's been a lot of recent activity on the Tate conjecture for K3 surfaces over finite fields. The recent activity, there's at least sort of three different proofs. There's Charles, there's Maulik, and there's Matapusi-Pera. So this is awesome. Q even is not going to be so good, but Q even is not so bad if you have to do sort of things. Yeah, well, Q even is fine. Let me not go into more details than that. Okay, so. Okay, so let's, before I tell you how to compute this characteristic polynomial and why this inverse is a little bit better, let me just take a step back and relate this to the original problem that I wanted to discuss, which was the K3 surfaces over number field. So let's say that, so if X is a K3 surface over K a number field, okay, and P is a prime of good reduction, some finite prime of good reduction. Okay, so then rho of x bar is less than or equal to, by this specialization argument, to the rho of my reduction at P, which is less than or equal to the number of eigenvalues of this sigma star inverse acting on this H2 tau x bar coefficients in QL of the form nu times q, where nu is a root of unity. Okay, so a little warning. So this number, and when I say this, I mean that number is even. Okay, why is that? So the real reason is that, so the eigenvalues that are not of this form, okay, so what are those going to look like? Well, the Weil conjectures tell us that the absolute value of these eigenvalues is going to be q. Okay. And they're not going to be q or minus q because I took care of the real ones in here. So they're going to come in complex conjugate pairs. And so that means that this number is going to be sort of 22 minus some set of complex conjugate pairs worth of eigenvalues that I need to throw out, and 22 minus even is even. So this number is even, okay, but this number could be 1. So at the end of the day, the best, if this is 1, the best we're going to get out of this is 2. Okay. So that's a bit of a bummer, but there's a fix. So we'll see that in a second. Okay, so let's start talking about this characteristic polynomial that I was promising you. So let phi q of x be this characteristic polynomial of this sigma star inverse acting on this H2 at x bar QL. Okay, so how do you calculate a characteristic polynomial? So this is now some nice finite dimensional vector space, and I have a linear operator on this finite dimensional vector space, and I want to calculate its characteristic polynomial. This is starting to feel like freshman year. And the way you would do that is, so if I actually knew enough traces of iterations of this linear operator, I could actually reconstruct the characteristic polynomial from those traces. So let me say that. So linear algebra, this is spelled out in the notes in gory detail, will tell us that I can compute, so phi of x can be computed from traces of powers of this operator. And by powers, I mean you just sort of iterate the operator. So this is something that this sort of linear algebra trick is usually attributed to Newton and Vieta. So it's not just classical, it's like ancient. And so it's not so difficult. It's sort of an elementary linear algebra thing. But this is good news. Okay? Because the Lefschetz trace formula tells us what the traces of powers of this operator are if I can actually point count on my surface. So the Lefschetz trace formula, what it says is that the trace of this sigma star inverse to the n, this is equal to the number of fq to the n points on x minus 1 minus q to the 2n. So this is the Lefschetz trace formula that comes out from the Weil conjectures. So, okay, this is awesome. So let's take one moment to take stock of what's going on here. If I can get a hold of these numbers by counting, okay, so at the very least we can just naively count. I have equations. This is over a finite field. you get your computers ready, fire them up, and count. Okay, so you count these things. That means I can compute the traces of the powers of sigma star inverse. This is why using sigma star inverse is so convenient. Once I have these traces, I plug them into this Newton Vieta formulas, and then I'm going to get the characteristic polynomial of this operator that I needed. And once I have the characteristic polynomial, I just factor it, and I look at the roots, and I look at the absolute values, and I see how many of the eigenvalues that are there are q times some root of unity. And there's my upper bound. So as long as I can count points, I'm in good shape. Okay, now, warning, counting points is hard. Okay, but it's getting easier. So these sort of, there's these techniques from the early 2000s that Kieran Kidlaya and collaborators have developed and really pushed quite a bit that allow you to compute these things using p-adic cohomology theories, at least when p is usually big. So let me be over q for a second, and so it's not so bad. The other thing though is there's sort of lots of little tricks that you can use. So for example, this thing was a 22-dimensional vector space. So if you look at the linear algebra that's involved, in theory I need traces of phi star inverse up to n equals 22, but there's some functional equation that comes from the Weil conjectures that this characteristic polynomial has to satisfy that'll immediately cut down the number of this n by 2, by a factor of 2. So I'll only have to go up to about 11. And if you know some divisors already in your surface, you can even cut down a little bit more. So there's some ways of getting around the troubles of point counting, but this is going to be sort of the hardest step, and I do not address that at all in my lecture notes, but beware, this can get tricky. Okay, but I mean, in some sense, we're still making very good progress. So let me just write an example. I don't think I've written really an example in the lecture. So x is going to be this, one of these K3s of degree 2. I'll do it over F3. And it's going to have the following equation. W squared is equal to 2y squared times x squared plus 2xy plus 2y squared plus 2x plus z times some homogeneous polynomial of degree 5. Okay, so this is some sextic. Of course, I have to choose this P5 so that this whole thing is smooth. That's not sort of a big problem. And if you apply, so I start literally, I count points on this thing, kind of naively. And if I count up to enough extensions, and I sort of do everything that I just told you, one over a finite field, let me not just worry yet about the number field, but over a finite field, then you can show that this row of x bar is in fact at most 2. So the number of eigenvalues of the correct form that'll come out when I apply this whole thing is actually going to be at most 2. So, okay, and in fact, you can also, various ways, Tate conjecture, this sort of thing. I mean, the Tate conjecture tells us that this should really be 2, but we can also see divisors on this surface. Namely, you see, so what is this x? Okay, x is a blob, and down here I have my P2, and there's this sextic. Okay, and the sextic is, the right-hand side of this equation equals 0. And if you look at the line 2x plus z is equal to 0. And if I intersect my sextic with 2x plus z equals 0, that goes away, and I get this nice square. So the line 2x plus z equals 0 intersects my sextic sort of with multiplicity 2, at least multiplicity 2 in every point. So it's what's called a tritangent line. Okay, so this is 2x plus z equals 0. And so when you pull back this tritangent line, what do you get? You get something like this. 1, 2, 3. Okay, and this like c and c prime. And you can look at the intersection pairing of c and c prime and show that they intersect as follows. And the determinant of this matrix is not 0, and so these things are linearly independent in my Picard group, or Néron severity group, whichever one you want to call it. And so this is a witness that this upper bound is actually sharp. So the Picard rank is actually 2 for this K3 surface. And now if I have a surface over Q that reduces to this one over F3, then I know that the Picard rank of my surface over Q is at most 2 already, just from this calculation. Okay. So that's pretty awesome. And I mean, look, concrete equations. I know I haven't written that many of them, but I love concrete equations. So, okay, great. So let me spend the last 10 minutes, or 9.5 minutes, telling you what to do about this pesky warning that I told you about, that somehow when we do this, I'm always going to get an even number once I look at the reduction mod P. I mean, if it so happens that, that rho of x bar is equal to 1 for a K3 surface over a number field, as looking at a single prime, at least the way we've set it up, isn't going to be enough with what we have developed so far. Okay. Now, this was actually a bit distressing because I mean, we know that over the complex numbers, so even if you look at algebraic complex K3 surfaces, sort of the general such K3 surface should have Picard rank 1. So things that have larger Picard rank actually form some countable union of divisors in the appropriate moduli space. And if you work over the complex numbers, you can apply the Baire category theorem and remove those things, and there's still something left. So we know that the general one should have Picard rank 1. But over a number field, I mean, we removed countably many things in this moduli space. Maybe we threw out all the ones that came from number fields. And maybe, over number fields, you couldn't have Picard rank 1. So this was a distressing situation. It was already, there were proofs by Terrasoma and Ellenberg that showed that these surfaces of Picard rank 1 did exist over number fields. But then Ronald van Lauk actually showed us how to sort of extend these methods a little bit and actually construct explicit examples of K3 surfaces over number fields that did have Picard rank 1. So say conquering rho x bar equals 1 over number fields, and this is some work of Van Lauk. So I'm going to take k equals q for simplicity, but I don't have to. And x, this is going to be a K3 surface. And then p and p prime are going to be 2 primes of bad reduction. So the idea is to use what we just learned, but do it twice, and look at how compatible the information is from 2 different primes. So here's the setup. Suppose that, okay, so Néron severity pick, they're the same, remember. So this is what, the rank of this thing is what I'm interested in. I know that when I have good reduction, my specialization will inject into this Néron severity of x bar. Yes, thank you. Yeah. Thank you, whoever that was. Okay, so I have these 2 injections, and suppose that we can show that this is, rank n, and that this is also rank n. How would we show something like this? Well, we do this kind of calculation that we already did to determine this n, and suppose that this happens. So this is the simplest situation where we would apply this method. And so if the discriminant of Néron severity of x p bar is different from the discriminant of Néron severity on x prime in q cross mod squares, then in fact, you must have that the Picard number of the original surface is bounded by n minus 1. Okay, so this is how we conquer 1. So what we do is apply this when n equals 2. Okay, so you find two primes of good reduction where you can prove that the Picard rank is 2, like this one, okay? And then you compute the discriminants, and if they're incompatible, then we could not have had Picard rank 2, we must have Picard rank 1. Now, why does this work? Well, so if it turns out that rho x bar has rank n, then this would be a full rank sublattice of both of these lattices, okay? And then these lattices would have to have a discriminant that would differ by a square. And so if they don't differ by a square, this could not have been a full rank sublattice. So the rank is at most n minus 1. So it's a beautiful, beautiful little trick. Once you put all of this together, then it actually is not hard at all to come up with K3 surfaces that you can write down that'll satisfy this sort of property. I mean, we're already halfway there here. I write a K3 surface over Q that has this reduction at 3, and I already know that the rank is 2. And then I look for some other K3 surface, say over F5 that has, sort of this kind of property. And then I, use the Chinese remainder theorem to sort of paste these two K3 surfaces and write down something over Q that reduces to this one when P equals 3 and the other one when P equals 5. And I apply this trick and I'm done. So that's really nice. So let me just say that, so there is one issue, which is we need to compute this discriminant. Okay. How did I compute the discriminant? Well, back here, in this case, well, the discriminant is 4 minus 9 is minus 5. So what I did is I exhibited explicit generators, and I looked at this lattice. And sometimes finding those generators can be hard. Here, this was artificially constructed so that I immediately saw 2 generators. But you might not have those. So let me just say that to compute this discriminant of Néron-Severi, so find explicit generators. And one of my project groups last night found out how hard it is to do this. And two, one thing you can do is to use the Artin-Tate formula. Let me not, this is sort of described explicitly in the notes. So Klosterman made this observation. And this thing is, this Artin-Tate formula will tell you what this discriminant is up to squares. Okay? And that's good because I only need to know what these discriminants are up to squares. So, and the Artin-Tate formula follows from the Tate conjecture. And the Tate conjecture is now known when Q is odd. So I can use this sort of trick once Q is odd. If Q is even, well, the point counting is not hard, but the discriminants could be difficult to compute. Okay, so let me just say that there's an improvement by Elton Hanzaniano on this technique that's actually quite nice, which is that if you look at this map, this injection that we had seen before coming from specialization, this has torsion-free co-kernel. Now, in a lot of, I mean, in general, we saw that we had an injection after I ignored the p torsion. So if you sort of tensor with z1 over p, I had this nice injection. And for that map, in sort of a lot of generality, the co-kernel is already torsion-free. So this is, I should really say there's some conditions, and the condition is p, it can't be 2 when k is q. So that you basically, it's a question about dealing with the p torsion in this co-kernel. But the reason this is good is that it's sort of an improvement that allows you to either use information only at 1 prime, because, so if you suspect so that this is not a full rank sublattice, that the rank is less, then you'll end up seeing some torsion in this co-kernel, and then, sorry, let me say it. So if this has full rank, So just like we were supposing here, if this says full rank, then I got a contradiction. So say this has full rank in here. So then you might pick up some torsion in the co-kernel, and then you sort of want to make sure that the sort of things don't lift. So I'm not saying this particularly clearly. It's much better in the notes. But my clock just went completely red. So let me say that I want to talk just a little bit about a couple of improvements. So instead of going over, let me start here next time. I'll repeat this and say it more clearly, and then I'll move on to Brauer groups, which is the topic of the last 2 lectures. All right, thank you.